this video, we're going to be discussing spanning trees. What are spanning trees? Well, one of the advantages of trees is that they give us a few simple ways to travel through the vertices. If a connected graph is not a tree, then we can still use these traversal algorithms if we identify a subgraph that is a tree. First, we should consider if this even makes sense. Given any connected graph G, will there always be a subgraph that is a tree? Well, that is actually too easy. You could just take a single edge of G and voila. If you want to use this subgraph to tell us how to visit all the vertices, then we want a subgraph to include all of the vertices. We call such a tree a spanning tree. It turns out that every connected graph has one, and usually many, spanning trees. Let's take a look at what the definition is. Given a graph G, a spanning tree of G is a subgraph of G, which is a tree and includes all the vertices of G. Every connected graph has a spanning tree. How do we know? We can give an algorithm for finding a spanning tree. Start with a connected graph G. If there is no cycle, then G is already a tree, and we're done. If there is a cycle, let E be any edge in that cycle. And actually, let me draw this out to show you what I mean. So let's say, actually, let me move this a little bit. Let's say I have my graph here, G. And the reason I draw this graph like this is because you can imagine in here there are a bunch of vertices and edges. But let's just say we can draw it in this like region here. Well then, if this has a cycle, let's say we identify a cycle right here. There we go. This red cycle here is a cycle, and let's let E be one of these edges in that cycle, and consider the new graph where we just literally erase that edge. We still kept all the vertices. So this is the graph you get by deleting E. This is still connected since E belonged to a cycle. And so there are at least two paths between its incident vertices. Now repeat, if this graph has no cycles, we're done. Otherwise, find a cycle. So let's find using blue. Here's a new cycle. And let's just identify an edge on this cycle, and let's delete that edge. And then we rinse and repeat. Let's find a new cycle. Here is a new cycle in the green there. And let's just delete one of the edges. It doesn't matter which edge we delete. And then we just keep going. We found another cycle here. And we could delete one of the edges. And voila, we have found a spanning tree. So this process must eventually stop every time, since there are only a finite number of edges to remove. The result will be a tree, and since we never removed any vertex, it's a spanning tree. This is by no means the only algorithm for finding a spanning tree. You could have started with the empty graph and added edges that belong to G, as long as adding them would not create a cycle. You have some choices as to which edges you add first. You could always add an edge adjacent to edges you've already added, after the first one, of course. Or add them using some other order. Which spanning tree you end up with depends on these choices. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. All right, let's do an example together. Let's find two different spanning trees of this graph here. Well, again, there are two different algorithms for doing this. We could just start with a blank template and connect, or we can just delete edges one at a time by identifying cycles. And we're going to do that first. So first I notice there's a cycle here. And so I can get rid of any edge there and it would still be a connected graph. So let me just kind of squiggle out one of these edges. So that just means I deleted that edge. Let's identify another cycle. I see a cycle right here. And in that case, we can just delete any one of these edges. I'll do this one. Just delete that edge. Let's find another cycle. I see a cycle right here. And so let's just delete one of the edges. And again, it doesn't matter which one you delete here. It could be any of the edges in your cycle because it will still leave the graph connected. Let's find another one. Here's one. And we could delete an edge. Let's delete that one. And then let's see if I can find another cycle. I do find another cycle. There's one right here. That is a cycle. And so let's just delete that edge right there. I don't think I see another cycle, so let me redraw what this graph looks like once we finish this algorithm. So we still have this edge here, that edge, that edge, that edge, that edge, and that edge, and that edge. Are we done? Well, no, now that I drew this, I see that I still left in a cycle, and you can tell the cycle's right in the middle, so I'm just going to delete one of these edges. And so I should have deleted that edge. And voila, we have a tree. Yes, good. We have a tree. Now, that was one example. Let's do another example. In this example, we'll do a different algorithm. Let me, the computer's going a little slow here. There we go. So in this example, the way we're going to do this is we're actually just going to build the graph from scratch by just adding in edges into this vertex set here. Now I'm going to add in red edges to distinguish between vertices and edges. Now, we can add whatever edges we want, but we just have to make sure that we don't make a cycle. So we need to connect this graph without making a cycle. Now, my recommendation is try to find a longest path. Just literally try to trace out a long path, and voila, we're done. When you make a path, it's really easy to make a spanning tree. And then if your longest path doesn't hit every single vertex, just connect some leaves and you're pretty much done almost every time. That's my preferred technique. So although we will not consider this in detail, these algorithms are usually applied to weighted graphs. Here, every edge has some weight or cost assigned to it. The goal is to find a spanning tree that has the smallest possible combined weight. Such a tree is called a minimum spanning tree. Finding the minimum spanning tree uses basically the same algorithms as we just described, but when picking an edge to add, you always pick the smallest, or when removing an edge, you always remove the largest. So it just depends on which algorithm you use to find the minimum spanning tree. Again, that's only if you have weights. Anyways, thanks everyone, and I'll see you in the next video.